The universe is vast and wondrous. It is filled with celestial objects. Stars burn brightly for billions of years. Planets orbit these stars. Moons, asteroids, and comets populate this expanse. We look up and marvel. Among the most enchanting are the comets, often called dirty snowballs. They journey from the outer solar system, remnants from the dawn of our solar system. When a comet approaches the sun, its ices vaporize. This releases gas and dust, forming a glowing coma. The solar wind pushes this material away, creating iconic tails, a spectacular sight in our night sky. Observing comets teaches us about our cosmic neighborhood. They hold clues about the early solar system. But what if some comets are not easily seen? What if some travel in disguise? So what exactly are these mysterious objects we call dark comets? The name itself conjures images of stealth and shadow. A dark comet is essentially an old comet. It is a comet that has exhausted most of its volatile materials. These materials, like water ice, methane ice, and carbon dioxide ice, are what create a bright coma and tail. When these substances are gone, the comet stops outgassing significantly. It no longer produces that brilliant display we associate with active comets. It becomes a much fainter, darker object. Think of a regular comet as a piece of dry ice. As it warms up, it releases a visible cloud of gas. A dark comet is like that same piece of dry ice after it has mostly sublimated away. What remains is primarily dust and rock. This remnant core is still a comet by origin. It still follows a cometary orbit, but its appearance has drastically changed. It has lost its reflective, icy surface. It has shed its ability to create a bright, visible atmosphere when near the sun. It has become a ghost of its former self. These dark comets are also known as dormant or extinct comets. The term dark refers to their very low albedo. This makes them incredibly difficult to spot against the black backdrop of space. The most defining characteristic of a dark comet is its darkness. As mentioned, their surfaces are covered with a tar-like layer. This layer is composed of complex organic molecules and dust. These materials are very poor reflectors of sunlight. Some dark comets might reflect as little as 3 to 4% of the light that strikes them. This is darker than coal or asphalt. Imagine trying to spot a lump of coal floating in the vast blackness of space. It is an incredibly challenging task. This low reflectivity is their primary disguise. Another key feature is their lack of significant outgassing. Active comets are dynamic. They spew gas and dust, creating their signature comas and tails. Dark comets, having lost most of their surface volatiles, do not do this. Or if they do, the activity is very weak and sporadic. This absence of a bright coma makes them appear star-like or asteroid-like through telescopes. They blend in with the cosmic background noise. Let's paint a clearer picture by directly comparing bright, active comets with their dark, dormant counterparts. Imagine a vibrant, bustling city at night full of lights and activity. That is your typical active comet when it nears the sun. It announces its presence with a spectacular display. Its coma can grow larger than planets. Its tails can stretch for astronomical units. It is a beacon in the darkness. Astronomers can spot these comets relatively easily. Their brightness and distinctive appearance make them stand out. They are the celebrities of the small body population in our solar system. Now, picture a remote, abandoned village, shrouded in darkness. That is a dark comet. It has lost its bright lights, its bustling activity. It is quiet, unassuming, and blends into the surrounding landscape. Dark comets lack the extensive coma and tails. Their surfaces are not pristine ice reflecting sunlight. Instead, they are covered in dark, insulating material. This makes them incredibly faint. They are the hermits of the solar system. They travel their paths largely unnoticed. This difference in visibility is the most crucial distinction between the two. The source of their light, or lack thereof, is another key difference. Section 5. Hunting for ghosts. Evidence for dark comets. The idea of dark comets is not just speculation. There is growing scientific evidence supporting their existence. While directly observing a truly dark comet is inherently difficult, astronomers have found objects that fit the profile. These objects behave like comets in some ways but lack the typical cometary appearance. For instance, some objects discovered in asteroid-like orbits have later shown faint, sporadic cometary activity. These could be transition objects. They might be comets that are in the process of becoming dark, or dark comets experiencing brief awakenings. One line of evidence comes from studying the population of near-Earth objects, or NEOs. NEOs are asteroids and comets whose orbits bring them close to Earth. Scientists have found that some NEOs have orbits that are more typical of comets. These orbits are often highly inclined to the plane of the solar system, or very elliptical. Yet these objects show little to no cometary activity. They look like asteroids. These asteroids in cometary orbits are strong candidates for being dark comets. Their dynamics scream comet, but their appearance whispers asteroid. Section 6. The Silent Threat. Why dark comets are dangerous. The primary concern with dark comets is their stealth. Because they are so dark and exhibit little to no outgassing, they are incredibly difficult to detect. Our current asteroid and comet detection systems rely heavily on spotting objects that reflect sunlight or show cometary activity. Dark comets excel at evading these detection methods. They could be lurking in the shadows of our solar system. They might approach Earth with very little warning. This lack of advance notice is what makes them a potential hazard. Imagine an object several kilometers wide. It is made of rock and some remaining ice. It is traveling at tens of kilometers per second. If such an object were on a collision course with Earth, we would want to know about it. We would want years, preferably decades of warning. This would give us time to study it. It would give us time to potentially devise a way to deflect it. With a bright, active comet, we often get this warning. Its approach is heralded by its growing coma and tail, but a dark comet offers no such courtesy. It might only become visible when it is dangerously close. Section 7. Whispers from the past, near misses, and cosmic close calls. History, both recorded and geological, tells us that Earth is not immune to cosmic impacts. We have experienced close calls with comets and asteroids. These events serve as stark reminders of the dynamic environment we inhabit. While we cannot definitively say a dark comet caused a specific past event without direct evidence, the nature of such objects means they could have been involved in undocumented near misses. Their stealthy approach would leave little historical record unless they were very large or came exceptionally close. One famous event often discussed is the Tunguska event in 1908. An enormous explosion occurred over a remote region of Siberia. It flattened an estimated 80 million trees over an area of 2,000 square kilometers. The consensus is that this was caused by the airburst of a meteoroid or a small comet. If it were a small dark cometary fragment, it would have been virtually undetectable before it entered our atmosphere. Section 8. Eyes on the Sky. The challenge of detection. Detecting dark comets presents a formidable challenge for astronomers. Traditional sky surveys look for moving points of light. The brighter the object, the easier it is to find. Dark comets, with their incredibly low reflectivity, are exceptionally faint. They push the limits of what our current telescopes can see. Even large dark comets might appear as mere faint smudges, easily lost in the noise of data. It's like searching for a needle in a cosmic haystack, where the needle is painted black and the haystack is unimaginably vast. The lack of a coma or tail further complicates detection. Active comets are often identified by their fuzzy appearance. Automated survey software is programmed to look for these features. Dark comets, appearing star-like, can be mistaken for distant asteroids or even faint stars. Distinguishing a nearby dark comet from a more distant, intrinsically brighter asteroid requires careful observation and orbit determination. This takes time, a luxury we might not have if a dark comet is on a trajectory that brings it close to Earth quickly. To overcome these challenges, scientists are developing new strategies and technologies. Infrared surveys like the previously mentioned WISE mission and the upcoming NEO surveyor are crucial. Section 9. Conclusion. Vigilance in the cosmic dark. The question of whether dark comets pose a hidden threat to Earth is a serious one. The evidence suggests these objects exist. Their inherent characteristics, their darkness and lack of activity, make them difficult to detect. This stealth, combined with the potential for significant impact energy, means they represent a genuine, albeit uncertain, risk. We cannot afford to be complacent. The cosmos is not always a benign neighbor, it occasionally throws celestial curveballs our way. Dark comets are one such potential surprise. Understanding this threat is the first step towards mitigating it. Continued research into the nature, population, and orbits of dark comets is essential. We need to refine our models of how comets evolve and become dormant. We need to improve our detection techniques, particularly through advanced infrared surveys and innovative data analysis. The more we learn about these shadowy travelers, the better we can assess the actual level of danger they pose. Knowledge is our first line of defense in this cosmic game of hide-and-seek. Investing in planetary defense is not just about finding asteroids, it must also encompass the search for these elusive dark comets. Projects like NASA's NEO Surveyor Space Telescope are vital. They will significantly enhance our ability to find dark objects that could pose a threat. International cooperation is also key.